Well, good morning, and welcome to the latest installment of Mazzetti's Bending the Climate Curve learning series. I'm Christina Vernon Sanborn, Sustainability Practice Leader here at Mazzetti, where bending the climate curve is our mission. This morning, we're going to understand the infrastructure paradigm shift and how it will create opportunities for healthcare buildings. Walt, if you could share your slides.
Oops, I have to press the share button first, sorry.
Thank you. Next slide, please. Thank you. So this session is going to start to unpack the evolving infrastructure landscape, focusing on the changing electrical grid, advancing technologies, resilience needs, updated regulations, energy procurement, and finance. The shift in infrastructure is driven by changes in energy procurement, technology, regulations, and of course, climate. There's a growing need for on-site energy generation and storage for resilience, independence, and cost effectiveness. Long-duration energy storage now extends to heating and cooling, allowing facilities like hospitals to store these utilities for on-demand use, though this requires a broader understanding beyond conventional engineering. Some key topics we'll talk about today. About the grid itself, U.S. electricity demand is projected to grow significantly, impacting reliability and affordability. The challenges the grid faces, including capacity, aging infrastructure, severe weather, and the shift to inverter-based power. Storage. The National Consortium for Long Duration Energy Storage is working on technologies for 10 plus hours of electricity delivery. And some demonstration projects, including Valley Children's Hospital Energy Master Plan and Microgrid, and Kaiser Ontario Microgrid, which is the first renewable energy microgrid connected to a hospital emergency power system that integrates solar battery and fuel cells. And then, of course, regulations. Compliance with NFPA codes is essential for a safe healthcare facility. Walt Vernon is the CEO of Mazzetti, an employee-owned benefit corporation with offices across the U.S. and India, focusing on helping healthcare plan and implement carbon reduction strategies through the use of technology, infrastructure, and systems. He's also the founder and CEO of Sextant, a not-for-profit committed to developing sustainable infrastructure for health facilities in low-resource countries around the world. With degrees in mathematics, philosophy, engineering, business, and law, including an LLM in energy law, Walt is uniquely qualified to help healthcare organizations working on issues of carbon reduction. Next slide, please. Today's session will explore these 4 learning objectives, which are relevant for understanding the infrastructure paradigm shift. So first, understanding that paradigm shift. Next, recognizing the importance of on-site energy generation and storage. Then identifying key challenges and solutions for the changing electrical grid, and comprehending the role of regulations and compliance in healthcare facilities. We have applied for AIA continuing education credits for this presentation today, and will report attendance should credits be awarded. Please use the Q&A function of the webinar to enter your questions as they occur to you at any time throughout the presentation. With that, Walt, take it away.
All right, thank you so much. I thought I would start with just 3 book recommendations. Anybody who's been around me for very long knows I'm a reader. And some of the ideas that I'm going to start with, talking about the evolution of the power grid, I'm only going to be able to hit at a very, very high level. And so excellent books, anything by Daniel Yergin on sort of the international energy world. The Grid is a really fascinating, more recent book talking about, in particular, the electrical grid, which is a lot of what I'll talk about today. Merchants of Doubt talks a lot about how the vested interests in many ways are trying to obscure some of the things that we're facing. When I was a young engineer, just starting out as electrical engineering, I remember that when it came to energy, my job was usually to go to the building owner I was working with and to say, well, you could pick light bulb A or light bulb B, and here's the cost difference, and here's the utility cost, and so here's what your choice is. That was the full range of the design freedom, you might say, in the world of energy. I remember going into a utility company once, and they had a big sign up on the wall that said, "This isn't Burger King. We don't do it your way." And the world has come a long way since that time. And in many ways, this is one of the most exciting times to be an electrical engineer, I think, because today we're not really constrained by almost anything in some ways. As a profession, uh, the factors that we deal with in terms of the technologies that are available to us, the ways to buy the energy that we might be using, the regulatory environment, the ways we might buy stuff that either generates or stores or uses energy are all much more, there's many more flavors available to us in all of those areas, and all of them are changing. And so it's a very dynamic environment. And so I think uh, we as a community need to be designing not just technologies or not just procurement strategies or not just financing for our PPA. We really have to be thinking in a really different way, including how are the regulations evolving that are creating opportunities for us in healthcare. So I'm going to start with some reflections on the electrical grid, mostly to provide a context within which we can talk about the issues that are peculiar to healthcare organizations and the way some of those codes are changing and some of the opportunities that that's creating for us today, including a couple, as Christina said, of some demonstration projects. So I want to start with just sort of an overall assessment of the nation's electrical grid from this is a new report from the American Society of Civil Engineers, which embraces a broad range of infrastructure. And their most recent assessment of our collective US grid is a D plus. Um, and of course, all of us are well aware of the impact of AI and data centers on load growth in this country. And it's not just data centers, but there are growth functions coming from electrification of buildings, coming from certainly the electrification of the transportation system, um, growth of the economy in general. And so we are the designers of the electrical grid, if you will, are looking at really significant increases in demand. And if you look at this graph, you might notice, if you look at the time scale, that for roughly the last 20 odd years, um, load growth in electricity has been pretty flat despite our economic growth. And so we have sort of a way of operating and thinking, but we are about to face a very different environment. And that creates tremendous challenges for the folks who are designing the grid and trying to ensure its reliability. The grid, as we think of it, is not really just one thing. It is because of the way we have structured and organized elements of the grid in this country, it's really composed of a lot of different pieces, many of which are regulated differently and incentivized differently and come together in different ways, in a fairly haphazard way in some ways, planned as it could be. But I thought this quote was really interesting, that the grid that we focus on, and this is so relevant to us as we think about our opportunities as healthcare, it's formed as much from investment strategies and legal requirements as it is from technology. So generally speaking, when we think about the grid, and there's all kinds of variations and there's all kinds of exceptions to this, so it's just a very broad description. But we have generation, which is generally regulated at the state and local level, sometimes at the federal, depending on the resource, but generally state and local. Then we have the transmission of electricity, which is between states or regions typically. That transmission is really regulated in terms of reliability and economics by FERC and NERC, which are two federal agencies that you may hear about from time to time. And they have different things that they're trying to accomplish. And then in terms of permitting and where these things are able to be located, there are overlapping jurisdictions from state and local entities. So getting the electricity from wherever it's produced to someplace is a difficult proposition. And I'll make one note here about economics and sort of this particular relationship. One of the things when we think about the grid and how we design a grid, if you think about the transmission line from a coal plant, the coal plant is going to operate, at its peak, or can operate at its peak, and the transmission line can use its full capacity. And when we think about some of the renewable resources that are intermittent, if you think about it, those transmission lines have a different use characteristic because they may not be fully used most of the time. And so the investment in transmission could be problematic. And so I give you that example only to sort of suggest some of the difficulties that we run into in trying to manage a grid consisting of all kinds of different generation. There are organizations that are more regional called independent system operators, ISOs, that try to coordinate a number of different things. There is distribution then that happens from the transmission system to the building. Those are typically regulated at the state and local level in different ways in different states, which also makes it complicated because every state does it somewhat differently. And then, those of us who are designers of buildings, we deal with how are we able to use and even generate to some degree energy and certainly store on our premises. And that is obviously regulated. There is some federal, but state and local. So I give you this picture only to say that when we think about the energy system within which we work to design an energy system for a building, there are all these outside forces that are acting on us. And if you're an organization with facilities in many states, you've got a lot of variations of this to have to worry about. And as we think about, in particular, how we might be doing our procurement strategies, that can factor into how we want to move forward. All right. Hopefully that's useful. As we look at the evolution of the grid designers are facing a number of challenges. We have, in large measure, an aging set of assets today that comprise the grid. And so we certainly have that problem. We certainly have the problem of growing demand. And that growing demand and the aging problem intersect when we think about retirement, potential retirement of certain kinds of assets. So the generation and age is an issue. The transmission capacity and age is certainly an issue in a similar kind of way. And transmission is quite difficult to permit over long distances. We have an increasing incidence of severe weather, which is affecting both generation and transmission and the reliability of those assets during increasing amounts of severe weather events. I've had the fortune of attending a couple of interesting conferences this year, including IEEE had a conference on focused on, in a sense, the design of the grid. And this issue, it's interesting. You can be a climate skeptic if you want to, or think it's a political issue. But the people on the ground who are designing utility systems understand the reality that they're dealing with in terms of needing to design for the kinds of severe weather events we're starting to see. Christina mentioned the shift away from spending power to inverter-based power. That is creating some real issues in terms of grid stability, voltage stability, capacity. There's a lot of issues that are difficult to try to manage. Affordability is a huge, huge issue. I was at a conference of the California Energy Commission a couple of months ago, and this is one of the things that is highly on the front of their minds because, and there are implications of all of these things for us as designers, but they are really focused on how do we add this capacity? How do we add this transmission capacity. How do we harden our lines when electricity is already unaffordable in the state? The number of people who are behind on their electrical bills across the country is high and growing. And so how do we do what we've got to do to meet these needs? It's a really serious problem. And then I'll throw timing on top of that, because I think one of the audience members here gave a presentation that I heard, and I think it was his example that, I could design and build a new 5 megawatt data center in a year or two. But if I need to add 5 megawatts of capacity to an electrical grid between generation and transmission, that is a huge time problem. And so the out of sync nature of the growth versus our ability to react really complicates where we're going. Folks may have heard about the power shutoff in Spain, probably due to inverter-based energy. You've probably heard about the Moss Landing fires, large energy storage system in California. All of these, are pointers of the difficulty of moving quickly enough and effectively enough to ensure the grid that we all depend on. So one of the things they talked about in California, and this is sort of a lead in some ways to what I'm going to talk about in terms of healthcare facilities. In California, one of the things they were talking about is, rather than, the old utility paradigm was, well, we'll try to figure out how much load there'll be, and then we'll make sure we build enough capacity to generate it and transmit it to where it needs to be. That is one model. But if you think about that model, it means you're building a lot of capacity for the peak periods. And so it doesn't operate all the time, and yet you have to pay for it all the time, adding to the affordability problem. And so what the state of California is focused on is, how do we flatten demand? Instead of trying to increase supply, how do we flatten demand? And flattening demand is going to come from a lot of different ways, but among them is on-site generation and storage of energy in various ways, not only electrical, but other kinds of ways as well. So I'm going to shift now and talk a little bit about how energy systems in healthcare are evolving and what are opportunities, I think, for healthcare. All of us are facing, most of my clients will say, look, well, what we really care about is we need reliable power and energy. We need reliability and we need it cheap. Those are the two things. If you can help us with sustainability, that would be nice, but that's what we really need: reliability, low cost. And so those needs are changing for all of us as we think about health facilities. And increasingly, health facilities are important during severe weather events because they become the haven to which people come. And we have access to changing technology, changing codes, changing ways of paying for stuff. I'm going to focus on some evolution that's happening around electrical systems in particular, but then I'll finish with some reflections on other systems from the National Electrical Code and NFPA 99, the Health Facilities Code. So our traditional mental model for powering a healthcare facility is that we have what is on the left-hand side of this diagram, essentially an infinite, inexpensive utility grid. I've just shown you some of the factors that are sort of working on that grid, but that's been the presumption. And then we put a certain number of loads, we call them essential system loads, on a set of transfer switches, and we have an on-site, typically a cheap diesel generator capable of providing 96 hours of power. That has been our paradigm for at least as long as I've been practicing, which is an embarrassingly long time now. I do want to just make a couple of observations about this particular model. I did a quick calculation of the dollars per kilowatt hour that might result from this kind of a design when you're operating on the diesels. And so this is, these are approximate numbers, but you can see that the power that we produce from the diesel generators, all in, is in the range of $450 to $500 a kilowatt hour. Pretty expensive power. So that power is really obviously not there to provide power in the sense. It's really an insurance policy against failure of that infinite cheap utility. But it is worth reflecting on this cost as we think about potential paths forward. The other thing that I run into, I do a lot of work on, I sit on both NFPA 99 and the National Electrical Code, and I run into a lot of people who talk about reliability, that we got to ensure reliability. And the only way to do reliability is to have a utility we can depend on and a diesel. And I studied reliability science when I was in school. And, at a very simple level, the reliability of the probability of failure of two things is the probability of failure of one times the probability of failure of the other. And so you can see in my top little, this is the only math you have to know for this presentation. You don't even have to know it. You can just accept it, I guess. But that the probability of failure of both a utility, these numbers are average numbers from EPRI and other places, and a diesel at a plant is very, very low. It's like less than a thousandth, what is this? A thousandth of a percent. So it's very, very low. And that's good. And, that's the model we've been following forever. And so that's quite good. But one of the things that I think, as we start thinking about microgrids and systems built of small components that are hooked together like Legos rather than one big utility and one big diesel, is that we have a different reliability paradigm. It's not a one or one anymore. If we had a string of 10 fuel cells, was my example, even if the probability of failure is 1 in 10, because you have 10 of them, the probability of failure of the whole thing is infinitesimally small. And the opportunity for us to put together packages of on-site generation and storage creates an entirely different economic framework and reliability framework that in many ways challenges certainly current codes and also current practices. But the codes have been evolving. A number of years ago, we put in place a change that said, well, yes, the utility plus the diesel is the sort of the gold standard, but you could also, like a lot of colleges will have their own central plant that generates their own electricity. So they have an on-site source. And the code said, well, you could do that, and then you could use the utility for the backup power in that case. So our first evolution was to say, well, especially for those emergency loads, you could have on-site or off-site for either side of the transfer switch and the emergency loads. And then we said, an era came along where we started introducing time of use rates for electricity. And so hospitals they had these diesel generators just sitting there, and they wanted to run their diesels because they could then eliminate some of the demand charges from the time of use rates. So the codes evolved and said, or they wanted to put in a cogen system sometimes. Well, this is really emergency. So we put provisions in the code that said, okay, you can run your emergency systems all the time for whatever purpose you want. There's a list in NFPA 99, but basically we said you could do that. So now we had a system where you could have on-site or off-site on the normal side, on-site or off-site on the emergency side, and they can both run all the time, which starts to call into question, what's an emergency when, in a way. And then we introduced a thing where we said, okay, well, you don't only have to feed the essential system loads from your backup source. Now you could serve any load you want to from the backup source, as long as you segregated it from those loads that are required to have backup power. So now we have a system where you could have a utility or an on-site on either side of the transfer switches. Either one of them can run all the time. Either one of them can serve any load in the building. Then we said, okay, now we're going to open the door to more than just diesels. And now we're going to allow hospitals to put fuel cells, PV, batteries, microgrids, basically anything as a source of power on the emergency side of this equation. You could really already do that on the normal side. So again, all we've really done is expanded and said, look, you could have anything you want to on either side of the transfer switch. Uh, they can all run all the time and they can all serve any load you want to. The main distinction is we wanted to make sure we had 96 hours of on-site capacity so that if everything else failed, we could keep this hospital operating for 96 hours. People then started complaining, well, but CMS won't recognize these fuel cells. CMS won't let us do all of those things. So in 2023, CMS issued its categorical waiver. Hopefully everybody knows about this. The categorical waiver permits any hospital in the country to use the updated version of the National Electrical Code for their purposes only, of course. But you no longer have to worry that CMS is a barrier to anything. So they're now helping us, and that's a great development. So where we're headed now, let me just finish this. So sort of our next evolution was now we can share resources between the two sides of the transfer switch. So what you're looking at here is a microgrid with multiple pathways to the two transfer switches and to various loads. And so in many ways, our industry is able to have a lot of flexibility in how we design what's upstream of the loads here in terms of both generation and storage. The other thing that's happened, and I think this is highly significant, and I want to just talk about it for a minute, but there has been a lot of work in the National Electrical Code around demand factors and the ways we size our systems. This is increasingly important because as we move to all electric buildings, the rules around how we size our systems, both the buses, but also the on-site generation systems, are changing. And for a long time, the codes have permitted the emergency sources to be sized based on prudent demand factors and historic data. But they wouldn't permit that on the normal side of the transfer switch. And as I've just shown you, it's really difficult now to determine what's a normal side and what's an emergency side of a transfer switch. They both have all the same characteristics. You just have to make sure that you have 96 hours of capacity somewhere to serve the essential systems. But now, not only that, but you only have to size them for prudent demand factors and historic data. We're starting to see this happening in California on the emergency side, and this is going to provide us with ability to do much more economical systems that are going to have a much different design, I think. And this, by the way, for those of you who care about such things, this was just approved by the NFPA annual meeting last week. And so should go into print, I think later this fall. This will be the 2026 edition of the National Electrical Code. So this won't be enforced until your AHJ adopts it. But I know the state of California has said as soon as this gets published, they're going to adopt it as part of interim rulemaking. So an opportunity exists for all of us to get engaged in our code processes and get this thing adopted. Okay, so where we're headed is clearly a microgrid that can serve either side of a set of transfer switches that serve the essential loads and everything else. This is probably a 2029 evolution. I haven't quite got our committee there. And I will just say, I'll tell you one quick code making story. I've been pushing these things now for about 20 years in different ways, these codes, to move them to where they are today. And in one of my recent meetings, this is about a year ago, one of the guys I've served with for a long time on the committee said to me, Walt, you guys in California are fruits and nuts. We've been doing things the same way for the last 40 years. Why should we have to change just for you? And, you know, of course, we're not forcing anybody to do anything with these codes, but we are opening doors that I think can be really helpful to all of us, not just fruits and nuts in California. I want to shift gears and talk for a minute about the National Consortium for Advancement of Long Duration Energy Storage Technologies. I first heard about this at that IEEE conference a few months ago. And we have joined this consortium and are really interested in what's going on. It's a really fascinating effort by the US National Labs to advance the best policy and technology and thinking in the area of long duration energy storage for this country's benefit. And it's really inspiring and it's really important. And the work they're doing is really good. And they're doing work in a lot of different areas, whether it's regulations or finance models or technologies or market deployment or customer uptake. There's a lot of different things. And so I've been looking for actually, as we're working with customers now and clients and thinking about on-site systems for healthcare, how can we start to bring in some of the opportunities around long duration energy storage? And I did want to acknowledge that we've been talking a lot, or I've been talking, I'm an electrical engineer, exciting time to be an electrical engineer these days, but electrical is only one form of storage. We also have available to us thermal storage, mechanical storage, chemical storage. Chemical is sort of like the diesel fuel in a sense, or even hydrogen, as noted here. I think this slide came from the LDES Consortium's website. But I give you this slide to say we've been thinking about energy storage forever on healthcare facilities. We've just been saying, oh, it's diesel fuel plus essentially a transformer process to create electricity. And as we think about microgrids, as we think about energy storage, as we think about the reliability of power and or energy that we need in our health facilities, I do think we must be thinking in a more integrated way. We can't just be thinking about hooking stuff up to an electrical system and providing a big battery or a big diesel tank. I think the time has come to start looking at, rather than putting that chiller on the emergency generator, maybe we do thermal energy storage so that we don't have to generate electricity in an outage. And so to think about resilience in a much more comprehensive, holistic, and robust way, I think is going to serve us all very well into the future. And that needs to be the way we start to think as an industry and not the way that we have been thinking. I wanted to turn to a couple of examples of some of these ideas in action and just talk a little bit about some of the opportunities and challenges. This project, Kaiser, Ontario, happens to be, I don't know if anybody on the phone is from Kaiser, but this project was featured on the cover of the ASHRAE Decarbonization Design Guide for Healthcare. So thank you, Kaiser, for letting us have your image. This is, we think, the largest renewable energy microgrid for a hospital emergency system in the world. It's been operating now. I was on a call with the developer of the system last week, and he said it's been fully operational for a week now. So I guess it's 2 weeks. So it's an interesting project because it does include clearly an element of solar, a fuel cell system, and a battery system. And just a couple of observations about this. This particular campus system evolved over time. And so different elements were put in place at different times. It was not constructed as a single operating entity. And so there were different parties involved with different contractual relationships that had to be sort of put together as a part of the project. So the project wasn't just a technical solution trying to comply with regulations that weren't designed for this kind of a system. So not just designing regulation and designing technical, but also we had to figure out, really Kaiser had to figure out some of the other arrangements to make it all work in concert with each other. And this is not unlike the problem of a grid operator who has to deal with transmission from different sources and generation from different sources. And how do you put it all together in a way that's economic and that works reliably all the time? I think those same problems and opportunities, frankly, are coming to us as designers of the building systems. The other thing that I wanted to point out about this particular project is the physical dimension. So you'll see down in the lower right-hand corner, the battery yard. That particular yard, those green blocks there are the battery units, and they are sizable. And I think this particular system, I don't know if somebody from Faraday is on or not, but I think this particular system is designed to power the emergency system of the hospital for up to 12 hours. So that's good. But if a hospital needs 96 hours of capacity, and if you're going to factor out intermittent sources such as wind, that times 12 is what you would be looking at to sort of do the code minimum for a hospital. And that's a daunting challenge, which is why on-site electrical storage by itself is probably the wrong answer. Um, Although storage in general, space is one of the issues. And that's another issue, by the way, that the consortium is working on, is how do we compress more capacity into less footprint in a way to make these systems more feasible for use in the real world. This particular project was funded by the California Energy Commission as a demonstration project. And so we're quite excited about it because the notion is that these systems working together will be able to supply the emergency side of the transfer switch all the time. Now, with 12 hours of battery capacity, plus we have on-site fuel cells and solar, that should be no problem unless we had a major event that cut us off from natural gas to the fuel cells and left us only on the solar and the battery system. So the diesels are still there if we need them, but we anticipate that this microgrid will essentially carry the emergency loads for the hospital almost all of the time. And so it's a proof of concept almost. This other project, many of you probably heard me talk about many times. This is the Valley Children's Hospital. By the way, this is a rendering, but I got a photograph the other day. They've actually cleared the land, and you can see the shape of George as the solar panels are getting ready to be installed. And so that's quite exciting. This is another project that this one is completely funded by the hospital. So there's no grant money involved. And it was interesting. We actually got board approval, or we were about to go for board approval, and we had all the finances figured out, and it was going to work. We had designed a sort of a financing strategy to go with the technical strategy. And we were 2 days away from the board meeting when the news of the Inflation Reduction Act dropped. And so we had to stop the board presentation, redo all of the calculations. And then it was like a no-brainer, because with the Inflation Reduction Act, this, what was already a good project became a really good project. And now the provisions, of course, are somewhat in question, but this project would have worked even without the Inflation Reduction Act. Certainly not as well, but certainly it would have worked. And again, this project, like Ontario, uses a combination of methane-driven fuel cells, batteries, and PV to supply. We think it'll supply about 80% of the hospital, so it'll operate as a base load for the electrical system all the time, as well as the emergency system all the time, unless our natural gas line is interrupted to the fuel cells. And I point this out because if you think back to my slide on economics, where we looked at the economics of generating electricity from diesel fuel, which only operated in an emergency. So it was just a really expensive insurance policy. This particular microgrid, because it is operating as base load for the facility about 80% of the time and reducing their money, their expense, you have in the future two choices. We could buy an expensive insurance policy that almost never operates, and when it does, generates very expensive electricity, or we could consider a microgrid of multiple components with enough on-site storage and generation to do what the hospital needs it to do. And we can meet those first two goals, which I talked about. We can meet the reliability goals, we can meet the cost goals. And yes, on top of that, we can meet some of the sustainability goals. This particular microgrid is going to cut the greenhouse gas emissions for scope 1 and scope 2 of this hospital by 50% with the one project. So highly, highly significant project, and certainly something that can be replicated, I think, in a lot of places. I will say two things about this hospital. It does have a lot of land contiguous to it, as you can see. And not every hospital has a lot of land contiguous to it. And so that is, it does make this one different in that regard. The other thing is it was California, and in California, you would think we had high electricity rates, and we do, but they are buying transmission level power here, and they are buying it through direct access. So they're actually, their energy costs are quite low, and they're on a similar scale as that in some of the other states that we operate in, who claim that they can't do things because electrical costs are so low. So I put it out there that the main variable here that makes this one slightly a one-off is the space issue, not the electricity cost issue. So it's I think going to become increasingly feasible, particularly as, and I'll go back to my conversations about the grid. As I was talking, I was telling you about California saying they were going to try to flatten demand, because by flattening demand, they can avoid needing to build extra capacity or extra transmission. And one of the ways they can flatten demand is they can create incentive structures for people who are doing buildings like this to do on-site generation and on-site storage. Because if we're not presenting that demand to the grid, we are flattening that grid. And so a lot of talk, certainly in California, about mechanisms available through the CPUC or other entities to try to start to incentivize flattening the grid, which means for those of us who design on-site energy systems for a building like a hospital, which is mandated to have an on-site system, I believe the incentives will grow over time to be doing this kind of thing. And so that's when I started originally talking about the fact that not only are these things, there's more options available, but they're changing. I think that's a really critical thing to remember, because if we design a building with the assumption that everything for the next 30 years is going to be as we say, and maybe we throw an arbitrary 2% per year escalation or something on there, it ignores in some ways the seismic shifts that are happening around us and that I think are going to continue to create opportunities for us. So I think our designs really do need to be future focused as well as focused on economics, technology, et cetera. All right, so that's the Valley Children's story. And I wanted to end with this little story because I think it's a harbinger of the future. This is a little hospital. I think of this as almost the little hospital that could. This is a little rural access hospital in Goldendale, Washington. When a lot of us, when we think about PV panels or microgrids, people will say, yeah, but what about those little critical access hospitals? What about the little rural hospitals? Those guys, they don't have the resources. They can't possibly do what's needed in order to do this stuff. And these guys are proving that to be completely wrong. So this is a 25-bed rural access rural critical access hospital in a small town in southern Washington state. And the fellow on the left is I've come to really admire him. He's a really brilliant, super nice fellow. And he had a vision that he needed to upgrade his plant. And he wanted to do it in a way that was really future focused. And so he found somehow a technology for generating electricity through hydrogen fuel cells. And he determined that he was going to do it together with other associated upgrades that needed to be made. And so that thing behind him that you see is the hydrogen fuel cell. As far as I can tell, it is the only hydrogen fuel cell in the world that's supplying a hospital. I could be wrong. There might be some military or something somewhere, but as far as I know, it's the only one. And I do think there's a lot of controversy around hydrogen. When we wrote the ASHRAE decarbonization design guide, my review committee made me take all references to hydrogen out of the book. And it can be a controversial topic, but I do think, and I know the consortium is looking at hydrogen as a fuel storage strategy, because in some circumstances, it is likely to be a good fuel storage strategy. And this, we had to do a lot of regulatory work to get this permitted, but we did. This little thing sits right next to the central plant. If you can sort of see between the trees, some bricks back there, that's the central plant. And this thing's in a little shed next to the central plant. It can be done. It can be done in a hospital. It can be made to work. It can be done on the emergency side of a transfer switch. And in some circumstances is likely to be affordable and a good strategy, particularly as we move into the future. With that, I want to move to questions and answers, but I guess I would say this, leave you with one last thought. When I started as an electrical engineer, I thought it was my job to design a set of technologies, and I had everything else around me was fixed. And I believe that if we do that today, we are doing a disservice to those we serve, because not only is everything around us open to more opportunities than what I was open to with a utility who said, this is the cost, all of those opportunities are changing. And so this reminds me of when we were in algebra class and you would have to solve multiple equations with multiple variables. That's what we're dealing with now, except that the variables are also changing. And so doing this well, I think, will demand more of us as professionals than what we've done in the past. And I'm so excited to be able to be a part of it. And anyway, that's a quick overview. So happy to answer questions if there are any.
Thank you all. If you could go to the next slide. As a reminder, the Q&A function is through the webinar itself. You can type your questions as they occur to you. Just enter the questions there, and we will do our best to get to all of the questions before the end of our time. So our first question today is around natural gas. Natural gas costs seem to be going up. How is the fuel cell industry progressing to compensate for the increasing cost of natural gas in the future?
Great question. And I guess I would say go read the Quest in some ways. The energy markets are global and subject to so many variables. I will say that the fuel cell manufacturers are always working on improving their technologies in all kinds of different ways, including, of course, efficiency. There are some limits to efficiency for the fuel cells, of course. But they are also looking at ways to reduce the cost of their equipment. So I think they're doing that as much as they can. I will say that a lot of our electricity generation is increasingly also from natural gas. And so that's one of the interesting variables you have to think about when you think about building your models for projected cost for some of these things, is how are you going to assume that not only one fuel will change in future, but one fuel versus the other? Because if natural gas costs go up, so your fuel cell costs go up, it's likely that electricity costs go up, although probably at a different rate in a different way. So this is part of the complexity, I would say, of designing these systems and thinking through the elements that you want to include in what sizes. It's not a trivial, unfortunately, back of the napkin calculation anymore to design the right size of systems to anticipate these kinds of challenges. I don't know if that helps. The real answer is I don't have an answer, except I know the manufacturers are certainly working to make things better, and it's incumbent upon all of us to be aware of those things as we design our systems for our clients.
I have another question from an attendee, which is, hospital distribution systems are often designed to a peak of 20 watts per square foot, yet peak demand rarely exceeds 10 watts per square foot. The NEC is moving to a place where demand factors can be better utilized, but how can we push back against these oversized systems now?
Yes, I don't know if that came from a designer or from an owner. Unfortunately, today, we are constrained by whatever version of the code you're already under, which probably says, in essence, design an oversized system. And that's for an older system. As we start to electrify, that 20 watts a square foot number is going to go up even further. And the problem of oversizing versus actual will just be compounded. So it's a huge problem. What you could do, I think, is support adoption of the 2026 National Electrical Code by your AHJ as fast as possible. And it will include that language around historic demand factors, historic data and prudent demand factors. And then the question becomes one of interpretation. And how do you do that? And frankly, the design engineers are going to have to get accustomed to that. I remember, again, when I was a young engineer, the first time I went to my boss and I had done a calculation of a size of a hospital service, and I said, okay, here it is. And he said, that looks great, divide by 3. And I was shocked. And I almost couldn't sleep for about a year while they were building that thing, because I just knew it wasn't going to work, and it did. And, I think starting to live in a world of reality instead of brute force addition is where we need to be moving as a profession, where owners need to be demanding that their consultants move. And we're going to have to work carefully with our AHJs to do it in a way that works for everybody.
Thank you. Well, here's a question that I will answer. Can we get a link to the ASHRAE Decarbonization Design Guide referenced in the presentation? There are several on ASHRAE's site. That's true. We would be happy to include a link to the design guide when we issue the recording and presentation to today's attendees. So we'll be happy to take care of that. All right, next question. With increasingly degraded infrastructure and potential failure of that infrastructure, are we looking at a future where hospitals have to be islands that don't rely at all on the larger electrical grid?
That's a great question. And I would say one of the things that surprised me in the book, The Grid, they document the fact that in the rest of the industrialized world, Spain notwithstanding the Spanish outage, the number of outages and duration of outages is going down. But in the US, the number and duration are going up for all of the factors I talked about. But what I would say is a lot of people are working very hard in all kinds of ways to make things better. And most of them in ways that are not political, that are sort of beneath the political firestorms that happen. And these really, I think we are really fortunate to have some of the engineers and some of the thinkers focusing on this. I do think that it is healthcare and healthcare resilience, I think, is going to become also increasingly important in the future as we start to suffer from more severe weather events and the need for health care capacity especially in affected areas, but often in surrounded areas as patients are moved and people move will be strained. I don't think that we have to assume that we'll be islands, but we do have to be ready to be islands for some period of time. And maybe one other thing I'll say, I do a lot of work with FGI, and FGI a number of years ago wrote something they called the Emergency Conditions White Paper, which is a free document you can get off of their website. And part of what they talk through is how to think about the kinds of hazards that came out of COVID, but it was really broader than that. And thinking about what kinds of hazards are we likely to encounter, and how do we plan effectively for that from a facility perspective in particular. So that's another resource that's out there.
Thank you. Here's a detailed question about Ontario, so I'm not sure if you're the right person to ask this. But what is the sequence of operation in the Ontario electric plant during a utility outage? Are all the sources of site power in parallel all the time? Does the electric plant use closed transition automatic transfer switches?
Well, that is a complex and evolving question. I don't know if Jesse's on the call. Jesse could probably answer that far better than I could. And I, well, let me just say it's complex. It has evolved over time, and we continue to think about improving it. There have been a lot of complexity in this, but generally speaking, the intention is that on loss of power, the diesels will start up, the microgrid will start up, and the diesels will drop. The diesels will be the grid forming entity. The microgrid will take over and operate to the extent that it can, and only if needed will the other diesels kick back on. So I think that we are not perfectly there right now, partly for contractual reasons, I think. But it's a story in evolution.
And I'll add that we will get an answer from one of our engineers to supplement that answer and share that when we send out the recording and presentation from today. So look for that in your email, along with the link to the ASHRAE guide and the other materials. I have another question for you all. It's a compliment on the presentation. Thank you. As we look at the reliability of these microgrid systems and the electrification of our hospitals, the need for a different level and type of maintenance will be essential to maintain the reliability of these new sources of energy. What reliability is being designed into these systems to support maintenance? And we only have a few moments to answer this one.
It's the right question. And we are, I think, trying to build as much intelligence into the system as we can, especially for predictive maintenance, so that we can anticipate issues before they happen and deal with them even while the systems remain in service because of the modularity of the components. So it's a very real question, and it's one that people are paying attention to. And certainly if you design one of these things, it's got to be at the top of your list of considerations.
Well, I'm sorry we didn't get a chance to get to all of the great questions that have been asked. As with the prior question, we will seek an answer for the questions that haven't yet been answered and include that when we email the attendees today. So don't fret, your question will get addressed. Thank you, Walt, and thank you to all the attendees for the great questions today. If you could go to the next slide. Please mark your calendars for the next Bending the Climate Curve lecture series, a learning event on July 15th at 8 a.m. Pacific, 11 Eastern. Our speakers will be Jonathan Lewis from Klickitat Valley Health System in Goldendale, Washington, which was mentioned earlier in Walt's presentation, and Eric Sweet, Principal and Electrical Engineer with Mazzetti, who will explore the future of emergency power for healthcare settings. With that, I thank you for your time and attention this morning, and I hope you all have a wonderful month.